Welcome to Terrassa. My name is Arnau Reyes and I'm one of the team leaders of UPC Space Program, a team of engineers based in Universitat Politècnica de Catalunya. Our team was created in 2016 and ever since then, our main goal has been to bring all our knowledge to hands-on experiences. This is our 5th year participating in European Rover Challenge and we'd like to present you our rover, which is GAIA. Now we're inside the GAIA building, our main headquarters. So let's go inside and meet the rest of the team.
Robotic Arm Department builds a 6 degree of freedom robotic arm capable of manipulating objects and collecting samples from the Martian surface.
On the other hand, traction envelops the mobility system, which includes the propulsion, steering, and mechanism to adapt to the Martian terrain.
This is our frame and control department. Control develops the software that allows the rover to operate autonomously and ensures all systems communicate efficiently. And the frame part designs the chassis that connects all modules, ensuring and giving a solid yet lightweight structure.
The science department is in charge of formulating the hypothesis and studying the terrain on Mars.
The Grasshopper team is responsible for the development of an autonomous drone with object and surface recognition capabilities, working on both the structural design and the autonomous control systems.
The comms and marketing departments promotes the project professionally and through all the social medias. So you may be thinking why we want to participate at the European Rover Challenge?
Well, our main goal at UPC Space Program is to lead real-world engineering projects that are connected to our main passion, which is space. When GRAS started, we wanted to develop a fully autonomous rover, and finding the European Rover Challenge gave us the perfect focus for it.
Now we are working on GAIA, our 4th project, which has seen a huge improvement in this design.
From team organization to complex system design, manufacturing, testing, these are key skills for any engineer, and most of them aren't fully taught at university.
Yeah, and that's why we love the European Rover Challenge so much. It's not only about the technical side of things, but we're also working in a group and under pressure, which is very important for a day-to-day life of an engineer.
Our rover has been designed to answer one simple question. Can buildings be 3D printed on Mars? In order to answer this question, our team has researched high and low for information about printing 3D buildings, as well as the soil on Mars and how it can all be tied together. Our conclusion was that, using the method proposed by ICON and pushed by NASA in the project M-Impact, a building could, theoretically, be printed using the regolith on Mars as a base.
So, in order to verify our hypothesis, it all comes down together in our rover GAIA. The main core of the rover is composed by the frame and traction system together with the control system. Apart from that, we have the different detachable modules, which are the robotic arm, the Grasshopper drone, and the science module in the back.
So the chassis of the rover is divided into 3 submodules. First we got the power module, which gives energy to all subsystems, from the science module to a robotic arm. Then we got the control module, which communicates all subsystems, and then the robotic arm, which has the physical interface connecting the rover and the arm itself. Finally, the emergency button stops all actuators while still letting all communications flow.
The traction system starts at the control module, where our custom PCBs receive the set points via ROS2. These set points are sent to drivers with jack to each of the 2 degrees of freedom per wheel, the steering and the propulsion. Both of them are closed loop, and in the case of the steering wheel, we've got a homing system that allows us to know exactly where each wheel is in every instant, in order to make easier to the autonomous navigation to act in the rover.
So the control department is the department that creates the software necessary for the rover to move. We are divided in 3 parts. We have the graphical user interface, that is what the user is using while moving the rover. The second part is ROS, which is where all the computation is placed at, and it's what is necessary for the rover to move. And our third part is the physical boards, which talk to electronics and move the actuators.
This year, we developed an algorithm that enables the rover to navigate autonomously. A stereo camera runs a simultaneous location and mapping algorithm to estimate the rover's position in real time. Additionally, onboard cameras capture images of Aruka markers placed around the marcià, which are processed by the jet sonoring to provide supplementary odometry data and further refine the rover's location. Given a map of the terrain, A path planning module calculates the optimal route for the rover to follow. A trajectory control algorithm then ensures the rover remains on course from its starting point to the target destination. The stereo camera also plays a key role in hazard detection. If an obstacle is identified along the planned route, the path planning module automatically recalculates a new safe trajectory to avoid it.
This year, our team has made a special effort to design an autonomous drone. With the support from Atlas, a UPC Space Program team specialized in drone design, we are proud to present the Grasshopper. The Grasshopper's frame is fully 3D printable. Using a carbon fiber reinforced printable structure gives our team great flexibility to adapt the frame to various sensors and onboard computing components, while maintaining a low-cost, robust, and lightweight structure. For environmental awareness, the drone is equipped with a Raspberry Pi camera and an MTF-01 LiDAR. These sensors provide essential data for autonomous navigation. The data is processed by a Raspberry Pi 4 Model B, which communicates with the SpeedyVF7 flight controller to manage the drone's movements. At the heart of the system is a custom-designed PCB, which handles power distribution and radio communication. We've also integrated safety features, including an electronic circuit that automatically triggers an auto-landing sequence in case of communication loss, and a shunt plug that allows for manual power shutdown if needed. Our control department has already tested the autonomous systems using Gazebo and Rust2. Through machine learning, our drone can identify various color and shape probes, and accurately position itself using Aruco markers and image processing techniques.
The science department is in charge of creating and verifying the hypothesis. The science module is divided into 3 parts: the drill, the science survey, and the mineral composition box. The sensor module contains all the environmental sensors needed to verify if the area is suitable for a building to be printed, which consist of a pressure, temperature, humidity, UV light, solar radiation, and dust and particle sensors. The drill module contains our detachable helical metallic drill, which has the ability to collect and weigh subsurface samples. Finally, our sample collection box is a 3D printed chamber designed to weigh both rock and regolith samples, which will be collected using the robotic arm, ensuring precise and efficient sample retrieval. The box has been equipped with a servo, which gives the box the ability to be encompassed in complete darkness, allowing our scientists to inspect the sample composition based on the reflection of light from our LEDs. Additionally, in the case of finding liquid, our rover has been equipped with a pH sensor that will be lowered into a liquid using the metallic drill, allowing us to observe the potential of hydrogen.
The robotic arm is the main tool that we use at the competition. It's a 6 degree of freedom robotic arm, capable to lift up to 2.5 kilograms. It has a personally made microcontroller, and it's completely modular, allowing us to work either the GAIA or the robotic arm at the same time.
We are ready for European Rover Challenge!